you so much. All right. So yeah, so we're talking about these smoothing techniques where we're reviewing SMA 3, where we pretty much take when we take the average of the number, it's essentially the same as just taking this fraction here, like 1/3, and saying times this number here, and this number here. But what happens though if we have the same kind of situation and we want to change the weights, right? Like your grade for this course has certain categories, right? Exams are in this category. They weigh a certain amount. In-class assignments are in this category. They weigh a certain amount. It's not like I'm taking all of your in-class assignments, all of your quizzes, all of your exams, lumping them all together and then divide by 50 if you have 50 grades, right? I only assign a certain weight to that particular category. So remember the first day of class when I gave you the syllabus, I said the exams weigh 20% or whatever it was, I forget. Do you see, or I don't know if you guys went to high schools where they have weighted classes, like weighted courses. So it's possible for you to maybe graduate with over a 4.0, right? So if you take like physics or calculus or something, those classes, quote unquote, weigh more than like basket weaving or gym or something like that, right? So even though it may be a little difficult, there's this offset factor, right, that sort of helps to kind of level the playing field. All right, well, that's where we're headed today on this page here. What if you have situations where you have the same numbers themselves, but the weights are different? So hence what we're going to do is define this as, we're going to say definition, and we're going to call this the weighted WEIGHTED moving average, weighted moving average. I'm going to call that WMA. Okay, so we had SMA first, but now we're going to transition to something called WMA. We're going to say is a smoothing technique, that places various weights, in parentheses I'm going to say percentages. That's really what it is. We say weights, but weights percentages on our time series data. Okay. So whereas in SMA, I kind of do, because if I say it's an SMA 3, it automatically assumes the weight is 1/3. Or SMA 5, it assumes that those weights are equal, 1/5, 1/5, 1/5. But what if you have a situation where those weights are not equal? And I guess in terms of a real life situation, it may be that you want to place more weight on the data point that's the most recent, right? Because perhaps in the grand scheme of things, what matters yesterday, remember the time series is like time, like on the bottom, maybe in terms of your analysis, what data you observed yesterday is a little bit more important than data you observed 2 days ago or 3 days ago, right? So they don't have equal weight, but you distribute it based on something. Okay, so I'm going to say, I'm going to give us an example. And what I'm going to do, I'm going to refer back to the data. Remember the handout that I gave you guys last week that we were filling out together? I'm going to go back to that data there. So if you want to look at that data, or if not, I'm just going to write some of it on the board. It was like year and revenue. So let's see, I think it looks like this. It was like year. We started out with 1982, 1983. You can get the data there if you want it. 1984, 1985. And this was revenue here. Okay. This was the 1588. This is from last week if you weren't here. Just look at the handout from last week. And this was 1753. And this was 1408. And then it went all the way down to like 1990, 1310. Okay. Now, we did this SMA column last time where you had something like this. Now, the first thing here we ended up saying was what we call NA. We're not going to put a data in that first value there because once we start finding these first values here, we're going to start plotting in the middle of the time point. So you have something here, something here, something here. By the time you get to the very end, you also have the mirror image of this node 8 here. So you have one here and one here. Now, when we look at the WMA, so this is going to be a WMA3. This is going to follow the same structure as the SMA in terms of nothing here and also nothing here. Because with the WMA, we're also plotting in the center of the data window, right? So this mimics that in that sense. But now when we find these values right here, they're going to be a little bit different. And we're going to go over how to find these right here. Okay? But I just wanted to give you the structure of how the results are going to kind of play out. Now, so the window is still size 3. Now, be careful with this because often the most common error here is that when people start calculating a WMA column, they do it based on these answers right here, SMA. And make sure you don't do that. The SMA is based on the original data, and the WMA is also based on the original data. Okay, so just kind of act like this is not here when you're calculating these WMA values right here. Okay, so the first window of size 3, it still takes into account these first 3 points, as we do here. But the only difference is I have to give you the weights. You don't have to guess. If I ask you to do a WMA, I'm always going to give you the weights. So think about this problem here. If I say something like, if I say something like example 1, let's say example 1. And let's say I say perform a WMA3, a weighted moving average 3, on the data if 1/2 is used for the most recent data point, 1/3 is used for the second most recent. Okay, so this says perform a WMA3 on the data if 1/2, see now I'm starting to give you the weights or the percentages. 1/2 is used for the most recent data point. 1/3 is used for the second most recent. And 1/6 is used for the oldest. 1/6 is used for the oldest. Okay. So let's see here. Before we continue, there's one other thing I need to show you about these weights. When I did the SMA3, I said 1/3, 1/3, 1/3. All of those, like when, okay, so let me do it this way. When I gave you the syllabus, what has to be true? Like I say, in-class assignments, 15%. Um, oh, you guys can't see? Can anybody not see me? Okay. Oh, okay. Atari, you may have to log off and log back in. Oh, okay. Okay, good. When I gave you the syllabus, I said this category was 25% of your grades, the exams 20%. What has to be true about all those percentages at the end of the day? Even though they're different, what better be true about those percentages when you finish considering all the categories? Ah, good, Ashley. They better add up to be 100%, right? Because the highest in the class is 100%. If you take any class and the professor gives you a syllabus and the percentages only add up to 90%, hurry up and run away from that, because drop it and go take it somewhere else, right? Because those percentages have to add up to 100. Well, it's the same thing with these fractions or these weights. So they don't have to add up to 100, but in their world, they need to add up to 1, right? So 1/3 plus 1/3 plus 1/3 is 1. These fractions that I give you, you don't have to check them. I'm going to always make sure that's the case. But in this case, for example, 1/2 plus 1/3 plus 1/6 better add up to 1. Okay. But again, I'm always going to make sure that's the case. But that's just a characteristic of those things right here. Okay, so let's see what's going on here. If we want to fill in this value right here, I'm giving you the 3 fractions or the 3 weights. The window is size 3, so I'm still considering these 3 points right here. Be careful at this question. Out of these 3 points, which one is the most recent? So think about where we are now, 2020. If I said, based on where we are now, which one of those 3 values here is the one that's the most
1753.
Okay, why?
Because
why are you saying that?
If you look at the year, 1984 is closer to 2020 than 1982.
Very good, very good. And see, it's tricky because you would think, no, that's at the top. That's the most recent. Well, yeah, that's a very good point. We look at the dates. This one is the most recent. So I'm going to have something like this. WMA 3, like for the first answer, we're going to say 1/2. See, 1/2 is used for the most recent, times 1753. See, that's the most recent in the window. Now, this 1990 is more recent than this right here, but I'm only making the decision in terms of what's more recent in the window that I'm looking at that particular time. Okay, now plus 1/3 is for the second most recent. So in this case, here we go, 1558. Plus, the next fraction is 1/6. Now, if every problem that you do, it's not always going to be 1/2, 1/3, 1/6. Again, I have to give you those. But, those are kind of easy to kind of deal with. In this case, the oldest point out of these 3 is 1588. 1588. So go ahead and use your calculator and see what that is. See what that answer is there. Let me go get my calculator. I'll be right back. And let me know what you get. And maybe let's do, I don't know. If it's any decimals, just take it 1 decimal place or something like that. Just take it 1 decimal place. And you should be able to do, I would just put it in as a fraction, like 1. You should be able to just put it as a fraction, 1/2 times 1753. Well, you guys know how to do fractions. Let me know what you get once you see what this equals. if you get something, just put it in the chat box so I can see what you guys get. Anybody? Okay. Okay. Yeah, I think that's it. 1660.5. 1660.5. But notice what we did. We took that fraction, that fraction, that fraction. Now, be careful though, because some people still manage to do something like this. They'll get this answer, this answer, this answer, and then once they get everything, then they'll divide everything by 3. No, don't do that. Don't do that. Because see, you're like mixing in this one and this one, SMA 3. Once you get this fraction here, this fraction here, this fraction here, that's it. You don't have to divide everything by 3 like SMA. Okay, so now let's go to this value right here. Well, how do we get it? The window is still size 3. So what I'm going to do is now take this window like we normally do and shift it down 1. So let me erase this. I'm going to shift it down. Now this becomes our focus. See, it's the same thing we did with SMA. The window is still size 3. You shift it down 1. But again, we have these same fractions we're going to use on calculating this right here, right? So let me write this down. Same fractions. But now we shifted the window. 1/2. Now which one, what do you think? Let's see. Isabella, what do you think is going to go here right now? See, I shifted it down 1. Now I'm going to do 1/2 times something, times 1/3 times something, plus 1/6 times something. Isabella, any idea what's going to go in here?
1408.
Very good. 1408. And then everything else follows suit. Because again, and now in this window, the most recent value is the 1408. Okay, so then it's going to be 1753. So, and then this is 1558, right? So now this 1588 that we had before is now out of the picture. It's gone now. So now we have this right here. So if everybody could get the next 2 points, find this one and find this one, I think we'll be good to go. Find that, the next one, and then find the other one, and then we'll see what you get. So everybody's working on getting those next 2 points there. And I didn't put that other point there, but I'm assuming you guys have the handout from last time. It was 1986 and then 13. Oh, 1990 was 1685. This was 1310. Okay, let's see. Faith, did you get anything for this one right here? When you did it? What did you get for that one?
I didn't get anything for that. I'm a little lost.
Okay, are you understanding where it's coming from? Like, do you understand where this comes from in the grand scheme of things?
Yeah.
Okay, so then just make sure you have, so your calculator is just a matter of saying, like, you know, 1 divided by 2 times 1408 plus, and then just put that whole string in there, then we'll be able to get that there. So keep working on that. Keep working on that. Sophia, did you get anything for that one?
Yes, I got 1548.
1548? Okay. I think that's correct there. So if you guys not understand where this comes from, just keep working on your calculator, you know, to figure out, you should be able to just put this whole string in the calculator without turning this to a decimal and all that stuff there. Okay? All right. Let's see, Dana, did you get anything for this one right here? Are you still working on that one?
Plugging that one in right now.
Did anybody get this one yet? Anybody get this one? Yeah. Yeah, was that Talia?
Yes, I got 1416.5, which is also in the chat. Someone agrees.
Oh, okay, 1416.5. Okay, good. All right. Okay, so essentially what I do, I took this one, I shifted it down one, and now these new fractions here, or these new values here, become the ones of focus there. So this technique is really self-explanatory, right? I'm just using weights to do those. Now, of course, when it's time to graph this thing, and we're not going to graph it right now, we'll give it take a break in a second. We graph this thing now, I'm going to have 3 lines: the original data, 3, and the WMA3. So it's going to look real convoluted. It's going to look real convoluted. But the main thing to recognize is that when I plot this point here, you know, I just need to make sure I don't plot anything on the first value there of 1982. I think I was noticing some of that when I was looking at some of your, I think it was a lab we had for, I don't know, I forget what it was. But just be careful where you guys start plotting these things. But this one and this one, you leave blank here, blank here, blank here, blank is like a mirror image, right? If you have an SMA 5, then 2 are blank here. I won't torture you and ever give you a WMA 5. That means I have to give you 5 different fractions, right? And that's just too much. That's just too much. So I may give you an SMA 5, but I will never give you a WMA 5. The most I give you for a WMA is 3 different weights. Although the weights could be different, as long as they add up to 1, that's all that matters. Now, after the break, we're going to look at another technique, another smoothing technique, where there's going to be answers at every single one of these points. It's not going to be an NA here or an NA here. Every single value or every single place in that in the last smoothing technique is going to have an answer. So it's going to be answer, 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 answer. Yeah.
For the last one, I keep getting 1513.
For this one right here?
Yeah.
Okay, how did you set it up? You said 1/2 times.
I did 1/2 times 1685 plus 1/3 times 1310 plus 1/6 times 1408.
Okay, yeah. So in this case, see, this 1685 is for 1990. I just skipped. I didn't put the whole chart there. So the next point was the 1310, right? So when you take this window and slide it down, you stop here at the 1753, 1408, and 1310.
Oh, okay. I was originally doing that, but then whenever you filled in the last one, I got confused.
Okay, yeah, that was just because I made an error. I think I put 1310 down here at first, and so the 1310 is for this right here. So the next window is for these right here.
So you wouldn't even touch the 1990?
Yeah, you wouldn't touch the 1990 until after you get to 1987, 1988. But I just left these off just in the interest of space. So this like a dot, 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 and the last one was 1685. So what you do is that you keep going, and eventually you will get to 1685, but that answer would be like down here somewhere. You know, it'll be the last one right before the NA.
Okay.
Yeah, I just end up skipping some values there. So this last smoothing technique we're going to look at is, so we're going to do this last smoothing technique, but we're also going to be able to use it to predict. So that's where we're going to go now. We just kind of finished with page 503 and 504 if you want to take a look at those, but it tells you about how to assign the different weights to different ones. So if you guys are still having challenges with putting in your calculator, how to get those answers, keep working with that. You have a chance to do that. Now this last one that we're going to look at is called, I'm just going to add a word, the exponentially, so like exponent, exponentially weighted moving average. I'm going to call that EWMA. Okay, EWMA. If you guys have been looking on the news stations when it's like tracking the coronavirus, I saw something really interesting. They have the little data to show like the spike in cases, and then there has something like 7-day moving average. I thought that was very interesting. That I saw that on TV because we just got finished talking about that last week, and that moving average is what we did last week, SMA, and they would just look at have a window of size 7, and then just they'll have that line sort of going through there. So like people do this stuff in real life. All right, so the exponentially weighted moving average, EWMA, is a smoothing technique that applies. Okay, so it is a smoothing technique that applies weights. So we're still going to have these weights to the original data. Okay, so that applies weights to the original data and previously. Okay, so that applies weights to the original data and previously smoothed data. Okay, so this says EWMA is a smoothing technique that applies weights to the original data and previously smoothed data. Our window size is always 2. All right. So, and you may be saying, well, when do you use which one? You have 3 of them: SMA, WMA, EWMA. Well, it really depends on what the goal of your mission is in smoothing, right? I guess like for stocks, I don't know, maybe perhaps you want to, with stocks, and I know it's not a finance class, but again, like WMA, you want to focus more on what happened with yesterday's stock versus 2 days ago, so you kind of change up the weights there. This one, I guess, is used in a lot of business circles, but it depends on if you want to use a cumulative effect of the data that you have. As opposed to just data with like previous days, for example, it can have, you could be looking at data that has yesterday's value in it at the same time while you're looking at 2 days ago. I'll never get into asking you why would you use this technique or the other one. Let's just make sure we can clamp down on the actual algorithm itself. Now, what I'm getting ready to write here is going to be it's going to seem a little tricky, but I promise you it's going to get a clearer as we move on. but just trust me as we're doing the algorithms, and we'll explain it when we do a problem. So here's how the algorithm goes. In other words, how to calculate the values in the EWMA column. So the first thing we're going to do, we're going to say EWMA. I'm going to put a little 0 right here. And I'm going to explain what that means in a second. Equals y sub 0. This 0 is sort of like a subscript. You know, it's not y times 0, but like y of 0. And essentially, this is going to be for like t equals 0. And I'll talk about that in a second. The second part of the algorithm looks like this. EWMA. I'm going to put a little t right here. And I'll explain that in a second. Equals. All right, here we go. This is a Greek letter. It's called lambda. And look on page 505. If you look on 505, they may draw it a little better, right? But we'll talk about what that means. And I'm going to say y sub t plus 1 minus lambda. So you have lambda right here and 1 minus lambda. And then EWMA. And then this says t minus 1. Let me write that a little clearer. EWMA. And then the little subscript here says t minus 1. Okay. And we're going to talk about this in just a second. So now this part right here is going to be for t equals 0, time equals 0. And then this part of filling in the EWMA column is going to be for t equals 1, 2, all the way to the end. So this is 1, 2, dot, 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 dot. I'm going to try to explain this as we move on. But just make sure you can at least have these two parts of the algorithm. Again, it's on page 505. Yes.
Can you say what that says again in parentheses under EWMA on the right?
Yeah, so this is t equals 1, comma, 2, comma, dot, dot, dot. So this first part here is when t is equal to 0, when time is equal to 0. And then this part here, we're going to use when time equals 1, 2, 3, 4, all the way to the end. So dot, dot, dot just means so forth and so on. Okay?
Thank you.
All right. So everybody just kind of stare at that a little bit. Because I'm going to erase it in just a second. Yes.
Right where below where it says size, that's t equals 0.
Yes. Yes.
Is that part of the formula that you just wrote out?
Yeah, that goes with this part over here.
Oh, okay.
And this t equals 1 goes with this part right here.
Okay, thank you.
Now we need to figure out what this mess means. So I'm actually going to write this over on the side so I can have it. I'm just going to, just give me 1 second. EWMA 0 equals y0. And EWMA t equals lambda yt plus 1 minus lambda EWMA t minus 1. Okay, I just need to write that because I'm going to erase this right here. Yes.
Can you please repeat what's in the parenthesis next to the arrow pointing to the first one that you're about to, yeah, that one.
0, t equals 0. All right. So that was t equals 0. Okay, so let's define, let's see, the best way to do this, I'm not going to write, yes I am. Okay, so when I have EWMA 0, that is the first value in the EWMA column. Okay, so I'm going to do the same problem using the same revenue values in a second. So we're going to have the year 1982, blah, 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 blah. then we're going to have revenue, the original data, then we're going to have the EWMA column. Now, the first value in that column is going to be what we're calling this EWMA 0, right? So there won't be any NA columns or NA variables in this thing here. Now, what I'm going to call Y sub 0, I'm going to call this the first value in the data, let's say original data column. Original data column. Okay. So this Y0 column is going to be our original data. Like in our case, it's going to be revenue, right? Or it could be sales or whatever you're kind of monitoring in that time series problem. That's what we're going to call the Y. All right, now EWMA with the T is going to be the exponentially smoothed value. So this is the exponentially smooth value at time t. See, that's what that t is right here. Now this first thing right here, this says the first value, so it's really the exponentially smooth value at time 0. And we're going to see what that looks like on the chart itself. It's going to equate to the first value in that particular column, and we're going to see why. But this thing right here simply says it's going to be exponentially smooth value at time t. That's just kind of what it means. Now, this lambda right here is called something like the smoothing coefficient. Okay, so this says smoothing coefficient. And it's the same thing as the weight. It's just a real fancy term for saying it's the weight. So in this problem, I have to tell you what the smoothing coefficient or the smoothing parameter is. Sometimes you hear smoothing coefficient or smoothing parameter, and that's the part where I like give you the fraction. But often in EWMA, well, not often, all the time in EWMA, it's going to be given as a decimal. Okay, so don't worry about, oh my God, what is lambda? It's just going to be the decimal that I give you for the problem. It's like me giving you the 1/2, the 1/3, or the 1/6. Okay, and so we're going to see how this looks here. Y sub t equals the value of the original data. Okay, so this is the value of the original data at time t. Okay, so whenever we mention in the y, like y of this or y of this, it's always going to be that value in the original data, or in this case, revenue. Okay, and we're going to see something very interesting when we do this that we didn't do before with WMA and SMA. Okay, 1 minus alpha is just taking the value that I give you for alpha and just saying 1 minus that, right? So we're only going to have 2 fractions in this problem. The one that I give you, which is lambda, and 1 minus it. But notice that when you add those 2 fractions together, lambda plus 1 minus lambda, both of those fractions still end up being equal to 1. Finally, I'm going to put this up here. EWMA of t minus 1. Again, we're still a little confused, and I understand it. But just trust me. EWMA of t minus 1 is the smoothed value at time t minus 1. See, so this is EWMA, and there's like a little small t minus 1. That just stands for the exponentially smooth value or the smooth value at time t minus 1. T minus 1. Now, we're going to see in a second because we're going to do an example. Well, yeah, I'll wait till we do it then. But just make sure you have these in your notes somewhere so that on the exam or, well, I have to say quiz, we don't have any more quizzes. On the exam, you can at least kind of know what all of these mean, Now, let's jump into a problem, and I promise you once you get the hang of it, it'll be fine. So go ahead and rewrite the original data that we started with, 1982, 19, whatever. If you have those already, we just want to add a column. And just give me a minute to put these back up here. Okay, so this is year 1982, 1983, 1984, 1985, all the way to 1990. Now, this is my revenue again. It's my revenue again. But this is what I'm calling my Y. Eventually, when we get to the algorithm, so your original data is always going to be that Y column, what we're referring to as the Y column. So we're going to say 1588. Yes.
Professor, I don't know if you can do this, but is there any way that maybe we could write like all of the data out so that we're all on the same page with, like, I just feel like this is a lot of new stuff.
When you say write all the data out, you mean all of this stuff right here?
Yeah.
I just don't have the board space. That's not because if we were in the classroom, I would, but I'm trying to maximize like the board space. I mean, I can put like maybe one more here, but like
Okay.
unless I write on my wall, 1408, and then how about I just kind of stop here and then go to 1990? Because I just don't have the board space, and then this skips to 1685. But I think as we're going through, once you sort of see the pattern of it, you can sort of fill in the rest if you want to. Now, when we do it on Excel, of course, we'll do all the data. But I'm just really limited what I can put here. But if you look at, I think somebody said the folder from last week, all the data is there on the handout there. Okay, so I'm going to say EWMA. And so this is what we have to fill out right here. This is what we have to fill out. This new EWMA column. And so here would be what the instructions would say. And I'm going to go in the rest of that in just a second. And I'm going to go ahead. It will say something like this, example 2. It will say something like this. Smooth the revenue data using an EWMA, and I'm going to say lambda equals 0.6. So it would look something like this. Or you use the exponentially weighted smoothing algorithm, lambda equals 0.6, to smooth the data. Okay. So up here, I'm going to go ahead and say lambda equals 0.6. So that's kind of what that column would look like. Okay. So now, the first thing we have to do, see, these are the values that we have to fill in. That first one, that second one, that third one, right? So forth and so on. Now, how do we get this first value here? Now, when I'm solving this problem, I'm going to think about this right here. This is the t equals 0 that we mentioned before. So this is the case when time equals 0. It's always that first number. This here is time equals 1. See how the numbers keep increasing in terms of time? This is t equals 2. And so forth and so on. Even if this said Sunday, Monday, Tuesday, Wednesday. So what? It's still t equals 0, t equals 1, t equals 2. Okay? But this is just getting us ready to kind of solve the algorithm. Now, when I get this first answer right here, this first answer comes from the first part of the formula that looked like this. It looks like this. EWMA 0 equals y sub 0. You remember that on the algorithm that we wrote? It was two parts. This was the first part, and then the other was the second part. This answer here is saying in the column, in this answer right here, this represents EWMA when time equals 0. This is the answer for EWMA when time is equal to 0. This answer will always equal to what? In this case, look carefully. This answer here has to be equal to what in this case? EWMA when time equals 0 equals what when time equals 0? Yeah, who is this? Anna? Is this Anna? Oh, who's this? Jaylene?
No, Aileen, yeah.
Okay, what is that equal and why?
It equals 1588.
Why?
When we wrote it down, we said it equals the first value in the original data column.
Very, very good. So 1588. So in other words, watch this. EWMA when time equals 0, this value will always equal to the first answer, time equals 0, in your Y column or revenue column. So this answer equals this answer right here. See this? This is Y of 0, or Y of t equals 0. Here, I'm saying in order to get this, in order to start off the process, this answer right here, the first value of EWMA will always be the first answer in the Y column. Is everybody okay with that? Yes, always. Yes, always. The rest of these answers here come from the second part of the algorithm that I wrote. See, this was the first one. That takes care of that. The rest of these answers come when t equals 1, 2, 3, ... So the rest of these answers here, see here, because t equals 1, 2, ... is going to come from this second part. Now, let me write the second part over again so we can see what it looks like. Here's what the second part looks like. EWMA of t equals lambda times y sub t plus 1 minus lambda times EWMA of t minus 1. I hope you guys can see that. It's kind of EWMA of t minus 1 times EWMA of t minus 1. Let's work through this. Okay, we took care of t equals 0. The next value to consider for t is now 1. So this says this. EWMA of 1, t equals 1, equals lambda times y of 1. I haven't really done anything yet. I'm just putting in the number of the t that we're dealing with. Plus 1 minus lambda times EWMA. Well, when I put 1 here, this now becomes 0. See, my t is 1, so that's 1 minus 1 is 0. Now, what does that mean in this problem? What does that mean in this problem? Well, time equals 1 corresponds to this. EWMA of 1983 equals. See, this 1 here corresponds to the time period of 1983. That's the first one. Equals lambda times y also of 1983 plus 1 minus lambda EWMA of what year? Think carefully. Of what year? Yes. Who is that?
Katarina, is it 1982 because the T is 0?
Yes. Yes. Very good. Very good. Because now, did you guys see how when I write it like T's, 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 see, this is just saying one time period before. One time period before. Or 1 minus 1 is 0, and 0 corresponds to 1982. If this were Sunday, Monday, Tuesday, Wednesday, then this would like be Monday, 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 and then EWMA of Sunday. Okay? So in other words, you have to sort of keep handy how your time is given. Your time is not always going to be in years. All right. So now we can start. So this is EWMA of 1983, which is what we're going to calculate. So I don't have the space. I'm going to put it right here. EWMA 1983 equals. Now, what is our lambda in this problem? 0.6. So I'm going to say equals 0.6 times. What is y of 1983? What is y? Kiara, what is y of 1983 according to the chart? What value? Y of 1983. Any idea? Y, remember, this is the y column right here. Okay, all right, good. 1558. See, here's my y. 1983 is this number right here. So times 1558 plus. What is 1 minus lambda? You probably can see it without a calculator. Well, if lambda is 0.6, 1 minus lambda has to be 0.4. See, this is 1 minus 0.6. 1 minus lambda. And then finally, times EWMA of 1982, which is what? EWMA 1982.
1588.
1588. But which one? But which one? Which one? You see, we got two of them here.
It's the one under EWMA.
Very good. Very good. See, because what happened was, now I want to go real slow through here. This algorithm makes you use one of the values in the y column and one of the values in the EWMA column at the same time. See, before we were just saying window of size 3, slide it down. But in EWMA, I'm using one of the values in the y column and then one of the values in the previously smooth column. Okay? So everybody calculate this and see what you get for this. See what you get for this. 0.6 times this plus 0.4 times this right here. And we'll just go, I guess, just one decimal place. That's fine. I guess it's 1.5. Whoever gets something, just let me know. Is 1570? Just right, okay. 1570. 1570. So that's using the second part of that algorithm to calculate this. Let's keep going. Let's keep going. Because the next one is this right here, this value right here. So let me erase this. Now, which algorithm am I going to use? I'm going to go back to the second part of that same algorithm, which looks like this. Let me give me 1 second so we can know where to start. I'm going to use this one again. So that's the original formula.
Professor, why are you writing it up there? Is it just because you ran out of space?
Yeah. And I just don't want to write on my walls, at least not today. So in other words, I could erase all this stuff right here, but I don't think that'd be too wise because you need to see this right here and this right here. So I'm going to calculate this right here using the scratch work right here. All right, so now this algorithm here is the same one that we used to get this one. But now our T is 2. We're going up, and it's going to be EWMA of 1984. We're going to go to the next year. That equals to 0.6. See, our lambda doesn't change. It's always going to be 0.6. Now I have y of 1984 plus 0.4, which is still the 1 minus lambda, times EWMA of what year? 1983. See that? See, this year reference right here is always going to be one less than these year references right here. Okay, equals. So let's see here. Based on what we just said, let's see. Michael, how do I fill the rest of this in? 0.6 times what? Like what numbers go where?
Honestly, I'm not sure. I'm falling a little behind. I'm just trying to process it all still.
All right, no problem, no problem. Yeah, this can get a little. I think once you guys sort of get the hang of it, I think it'll sort of fall in place. Let's see, Cameron, any idea like what's it going to be times what? According to the chart. 0.6 times what? What is y of 1984?
1753.
1753. Okay, plus 0.4 times something. Does anybody know what that something is? What is that something going to be? Who is this? Is this Dana?
Yeah, 1570.
Okay, and where is that coming from?
That's the y value for 1983, which is t minus 1 since we're on 1984.
Okay, yeah, very good. So that's going to be my EWMA of that 1983. So 1570. 1570. And notice here, this 1570 is what we calculated the step right before it. See that? So in order to get this value here, I'm using this green and this green. You see how we're using two different values or values from two different columns. Yes? So this value here, when I'm trying to smooth it, is coming from the value right beside it and the value right above it that we just calculated. So you have to be really careful because if this value that you calculate is incorrect, it's going to have like a domino effect. So see what you guys get for this one right here. Anybody got that? And we'll just do one decimal place. $1679.8. Okay. So, I mean, you know, all these T's and T minus ones and lambdas, yeah, okay, that's nice. But at the end of the day, I'm just simply calculating the next value point based on the value beside it and the value above it. That's why when we wrote the definition, the window is only of size 2 because I'm only using 2 values to get the answer. I'm using one value right here and one value right here as opposed to 3, 3, 5, right? So the window is only of size 2, this number and that number right there. So there's 1679.8. In any questions? I know it's different. I know. I get it. I know. Do the next one on your own. Find the value for here. Find this value right here. Everybody find that value. Yes.
Professor, will we always be given what the lambda is?
Yeah, always. I have to give you that lambda. I have to give you that lambda. Just like in the WMA, I had to give you like those three fractions. Yeah, I'll always give you the lambda in the problem. Yes.
Professor, for the equation for the last one we just did, at the end, I'm not sure if I wrote this incorrectly, but is it E times EWMA 1983? Wouldn't it have to be, okay, never mind. I thought I wrote 1984 again.
Yeah, because EWMA in 1983 should be this one right here, that 1570.
Yeah. Okay, thank you.
Yeah. Let's see. Joy, did you get anything for this right here? Are you still working? You still working on that?
Yeah, I'm still working.
Okay. Tatiana, did you get anything yet?
No, I'm still calculating it.
Still calculating? Okay. I think you guys get the essence of it. You know, I don't want these symbols to frighten you, like lambda. Oh my God, a lambda. Well, okay, just put in what lambda is, right? But as long as you kind of get the algorithm going, I think you'll be okay with it. I think you'll be okay. Yes.
Would the answer be 1516.72?
Oh, let's see. Let me see. Did I do that one? You guys may have to help me out. Yeah, okay, that's what. Okay, so say it again. You got
1516.7.
Okay, all right. And just do me a favor. Tell me, you don't have to go through everything, but tell me the setup. So you have EWMA of 1985. Tell me what you've written down in terms of the initial equation.
Like with the numbers in it?
Yeah. So you got 0.
Yeah, so it's 0.6 times 1408, which I got from the 1985 of revenue Y,
Okay.
plus 0.4 times 1679.8, which I got from the EWMA of 1984.
Very good. Very good. Yeah. So since I'm on a color coding, so this red sort of goes with this value right here, right? So that's the 0.6 times this, then the 0.4 times that. There you go. Very good. I think you guys got it. Now, so notice here that when we do this column right here, every single value here will be filled in. Even when you go all the way down to the bottom, you're not going to have any NA, like an NA up here and an NA down there. This is the only smoothing technique where all of the values will have an answer for it, which means that when you graph it, it'll be just like this one over here. No skips and no empty values on the graph there. But notice, how was this process able to work? It was able to work because I always assume the first answer here is always going to correspond to the first answer right here. EWMA of 0 always equals y sub 0, and that'll get the process going. But for the rest of these, t equals 1, t equals 2, t equals 3, ... all the way to the end, I'm using the second part of the algorithm to fill in those particular values right there. Any questions? Now, before we go to Excel, I'm just going to show you something right quick. And in the interest of space, I calculated the last one. Like if you'll keep going, you'll keep getting an answer. Now for this last one right here for 1990, I did that one and I got, what did I get? Give me 1 second. that would be EWMA of, oh, okay. I did this and I got this. Of course, you don't have to do that. You don't have to do this. And I'm doing this for a reason. So if you continue, getting 1986, 87, so I skipped some in between here. But imagine if you keep going down here, this is the answer right here. Now, you can use exponentially smoothing to, of course, smooth. So what we're doing here is smoothing. But you can also use EWMA to predict. And what do I mean predict? What I mean predict is predict one time period in the future from the data that's given. So according to this graph, or according to this chart here, if I want to predict one time point in the future, that's really predicting for 1991. See how the data stops at 1990? If I can also use EWMA to predict one time period outside of the data that I'm given. If this is January, February, March, April, May, June, July, August, then the problem would say predict September's value using EWMA is always just a T+1 or a one-time point outside of there. So I'm going to show you real quickly how to predict using EWMA, and you're going to find out that it's real simple. But any questions just on this part right here? This is not prediction. This is just what's called smoothing. All right? So I'm going to say we can forecast. So I'm going to say something like this. And let me erase this part right here because we finished with this part here. I'm going to say we can also predict using EWMA by using, I'm going to do something like this, y hat, just wait, I know, of T+1 equals EWMA of T. I'm going to substitute this. So just look and kind of see what it looks like. Y hat. Y hat is just a term when we want to predict in the future. See this T+1 right here? That means I'm trying to predict one time point in the future, T+1, right? What I'm going to do is substitute this value here for EWMAT in the second part of the function that we're dealing with. So just follow me here. Just follow me here. Watch what I do. 1 second. All right. This is 1990. Okay, watch what I do. See if this makes sense. EWMA of T. I'm just going to rewrite the other formula that I had before. Okay, so what I just wrote right here, this was the second part that we were dealing with to solve how to fill in those problems there. But all I'm going to do is wherever I see an EWMAT, I'm going to substitute this value right here, right? So we're going to have this y hat T+1. And I'll never ask you to do what I'm doing right here, but I just want you to see something. Okay, so I substitute this value here wherever I see this right here. So I'm going to substitute this. I'm going to substitute it there. Lambda times yt plus 1 minus lambda. So when I substitute this right here in place of EWMAT, it looks like this. Or over here. Y hat T+1 minus 1. In other words, here's the EWMA of T right here. I substituted this part here, and then I still have a lingering minus 1. And so what does that boil down to? It looks something like this. Y hat of T+1 equals lambda times yt plus 1 minus lambda and just y hat t. The 1 minus 1 cancels out. And so we're going to find out that this right here is just simply equal to the last smooth EWMA value. So this part right here is what I'm calling the most recent EWMA value. Okay? Yep, I will. Yep. Okay, so in other words, here's what I wrote here. This is what I'm using to figure out how to predict, right? And what I'm saying is I'm going to take this part and substitute this part right here where I'm going to calculate one time into the future, t plus 1. And I'm going to substitute this value right here for that. So I substituted it right here. And I substituted it right here. Okay? And essentially, I'm going to show you what the bottom line is. In order to calculate one time period into the future, I'm going to take still the 0.6 times y sub t plus 0.4. And now this value here, notice how all these t's right here are on the same level, right? So I'm going to use the most recent, this is the most recent EWMA value, the last ones that I have there. All that means is this. All that means is this. You remember the chart that we had? You know, this was 1909, whatever, 1982. This was the revenue, I think it was 1588, whatever, here. This was also 1588. This is the EWMA column, right? So you remember how we had all this stuff here? And I said, in order to predict, so let's say this is 1991, which represents predicting one time point in the future. See this, t plus 1, right? So in this case, what I'm essentially trying to do is find this answer right here. You're saying, well, we can't do it. We don't have any more data. Like, this is our revenue column right here. It stops at 1685. Okay, so this is the EWMA column right here. Remember, I put that value right here, 1727.2. All this says is, in order to predict one time point into the future, I'm simply going to use the most recent Y value and the most recent EWMA value. That's it. See, before we were using this value here and the previous EWMA value to get that. All this says is to predict, I'm going to use this value here right above it and this value here right above it. Notice this t plus 1 is one time point in the future. It's based on the t in the Y column and the t in the EWMA column right here. So what do we have? We have this. Okay, everybody write this. Y hat of 1991. I'm predicting the value for 1991 equals 0.6 times 1685 plus 0.4. See, that's still the 1 minus lambda times what? 1727.2. This is the only time where when I'm calculating or when I'm trying to predict that these numbers right here are on the same level, the same t level. See, before I took the t in the Y column and the t minus 1 in the EWMA column. But when I'm predicting, I'm going to still use the same lambda and 1 minus lambda, but I'm going to use the t level of the Y and the same t level of the EWMA. Is everybody okay with that? Don't worry about all this. I would never ever ask you to tell me where it came from. Who cares, really? Okay? Just kind of focus on the fact that only when you're predicting will the YT value be the same as you use the YT value and the exponential smoothing value on the same time level. See there? I'm using both of these here, which are always on the same level, which is at the last point time I'm given in the problem here. What does this end up being? Anybody do the math on this? Let's see, what is this? Is it 1701? 1701? Okay. 0.9 or something like that. All right. So what's the bottom line? Just make sure you know how to smooth using EWMA and how to make a prediction. Unfortunately, we don't know how to predict 2 time periods in the future. We only use this when we want to predict 1 time point in the future, t plus 1. That's it, right? And we sort of go from there. All right, questions? Questions? I mean, this isn't too difficult, right? I mean, if you think about it, the reason I wait to do time series like toward the end of the semester is, well, number one, I know everybody's tired. And number two, it really doesn't take that much brain power. I mean, I'm not trying to be funny or whatever. I mean, as long as you can, like, you know, we're not using F tables, T tables, and you know, you're just doing this regular old calculator stuff, okay? So you're tired, I'm tired, so that's kind of why I wait to do time series toward the end. Any questions? Any questions? 172. Oh, that what happened was I did all of the ones that we didn't do in class just in the interest of time, and I calculated the 1727.2 outside of class, right? Because it'll be too much to keep doing all that stuff by hand, right? So I just assumed I skipped over and I just figured out what that last one was outside of class doing the different calculations there. So essentially I gave it to you. Yeah. Yes.
So do you need all of the years leading up to it, like up until the last one, to predict the next one?
Yeah.
Okay.
So you either need, yeah, so in theory the answer is yes, right? Because like you can't get this one until you get the one before it, till you get the one before it. But like on an exam, I may just save you that headache, and I just may give you like the last two in this column, the last one in this column and the last one in that column, say predict, right? Or if it's an Excel exercise, you should be able to get those like really, really easy.